Let's figure out the oxidation states for some more constituent atoms and molecules. So let's say I had magnesium, magnesium oxide, MgO. I'll do oxygen in a different color. So what are going to be their oxidation states? And you might know this already, but let's just look at the periodic table because it never hurts to get familiar with it. So we have magnesium. Magnesium has 2 valence electrons. It's a group 2 element. It would love to lose those 2 electrons. Oxygen, we already know, is one of the most electronegative atoms. It's so electronegative that oxidized has essentially been named after them. And we know that oxygen loves to gain 2 electrons. So this is kind of a marriage made in heaven. This guy wants to lose 2 electrons, and this guy wants to gain 2 electrons. So what's going to happen? The magnesium is going to lose 2 electrons. It was neutral, so it's going to have a +2 charge, hypothetically. And then the oxygen is going to have a -2 charge because it gained the 2 electrons. -2. So in this molecule of magnesium oxide, the oxidation state of magnesium is +2, and the oxidation state of the oxygen is -2. Now let's do a slightly harder one. Let's say we had magnesium. Let's say we have magnesium hydroxide. So hydroxide is OH2. OH2, right there, where there's 2 hydroxide groups in this. So what are the oxidation states going to? So my temptation would still be, look, magnesium likes to lose its electrons. It's 2 electrons, which would make its charge positive, its hypothetical oxidation state positive. So my temptation to say, hey, magnesium here would be +2. So let me write that there, +2. And remember, in order for all my things to work, everything to work out, if it's a neutral compound, all of the oxidation states in it have to add up to 1. So let's see if that's going to work out. Now, oxygen, my impulse is that its oxidation state tends to be -2. So let me write that down. -2. And hydrogen, when it's bonded with an oxygen, remember in this case the hydrogen's bonded with the oxygen first, and then that's bonded to the magnesium. So the hydrogen is bonded to an oxygen. Hydrogen, if it was bonded to a magnesium, you might want to say, hey, maybe it'll take the electrons and it'll have a negative oxidation state. But when hydrogen is bonded with oxygen, it gives up the electrons. It gives up the electrons. It only has 1 electron to give up, so it has a +1 oxidation state. So let's see. At first you might say, hey, I'm adding up the oxidation states. +2 -2 is 0 +1. I get a +1 oxidation state here. That doesn't make sense, Sal. This is a neutral compound. And what you need to remember is, oh no, but you have 2 of these hydroxides right here. So what you do is you figure out the oxidation, the sum of the oxidation states of the hydroxide. So that's -2 + 1. So for the entire hydroxide molecule, you have a -1 sum. And then you have 2 of them, right? You have 2 hydroxide molecules here. So the contribution to the entire compound's oxidation state will be -1 for each hydroxide. But then you have 2 of them, so it's -2. And then +2 from the magnesium in your oxidation, and it all adds up to 0. So that worked out. Now, I want to do a little bit of a side. I want to go back to doing some problems again. But I want to do a little bit of side on some of my terminology, because I've kind of used oxidation state and oxidized and reduced interchangeably to a certain degree. But let's say, we've done so many problems with water, auto-ionizing into, actually, let me do 2 moles of water. And it's in equilibrium with 1 mole of H3O plus OH minus. And obviously everything is in an aqueous solution. Now, let's look at the water. What are the oxidation states in this water right here? Well, we've done this already. Previous video. Oxidation state of oxygen is -2 because it's hogging the 2 electrons from the 2 hydrogens. Each hydrogen is giving up an electron, so it has an oxidation state of +1. And we see this molecule, everything adds up because you have 2 hydrogens with the +1, so that's +2. +2 -2 for that 1 oxygen, you get to 0, and it's a neutral compound. Now here, what are the oxidation states? So one of these hydrogens left one of these water molecules without without, and joined the other of the water molecules without taking its electron with it. So it left the electron over here. So that oxygen still has a -2 oxidation state. And this hydrogen still has a +1. And that's why you do -2 plus 1, you get -1. And this time it works out because that's the actual charge on this hydroxide ion. Now, here, what are the oxidation states? Each of the hydrogens have a +1, oxidation state. And then this oxygen has a -2. And so if you look at the charge for the entire molecule, +1 on 3 hydrogens, so that's +3. I just added them up, -2. So I should have, so +3 -2, I should have a +1 charge on this entire molecule, which is the case. Now, my question to you is, has any of the oxidation states changed for any of the atoms? All of the hydrogens here, and we could call this, 2 moles of water, or like maybe I just said 2 molecules of water. But I have 4 hydrogens here, right? And all of them had an oxidation state of 1. On the right-hand side, I have 4 hydrogens. All of them have an oxidation state of 1. So although their oxidation state is 1, in this reaction, and you can pick either direction of the reaction, hydrogen has not been oxidized. Its oxidation state did not change. It stayed. Maybe it was oxidized in a previous reaction where the water was formed, but in this reaction it was not oxidized. Likewise, the oxygens, we have 2 oxygen molecules here, or atoms here. Each have a -2 oxidation state. Here we have 2 oxygen molecules. Each have a -2 oxidation state. Due to this reaction, at least, no electrons changed hands in our oxidation state world. So this is not an oxidation or a reduction reaction. And I'm going to cover that in detail in the next video. And I just want to be clear that nothing here was oxidized or reduced because their oxidation numbers or their oxidation states stayed the same. And I just want, because sometimes I'll say, hey, look, magnesium has an oxidation state of +2, and oxygen has an oxidation state of -2. Magnesium was oxidized. 2 electrons were taken away from it, and oxygen was reduced. 2 electrons were given to it. And I'll say that implying some reaction that produced it, but that's not always the case. You could have a reaction where that necessarily didn't happen. But the oxidation state for magnesium is definitely +2, and the oxidation state for the oxygen, or the oxidation number, is -2. But I think you know what I'm talking about when I say it was oxidized. At some point, it went from a neutral magnesium to a positively charged magnesium by losing 2 electrons, so it got oxidized. Now, let's do some harder problems. So hydrogen peroxide. I've said multiple times already that oxygen tends to have a -2 oxidation state. This is -1. I think you see the pattern. This is plus. Well, these guys are +1. Hydrogen is plus or -1. These guys are +2. I think you see the pattern. It's whether you want to lose or gain electrons. So you might say, well, let's see, water normally has a -2 oxidation. So you might be tempted to do, okay, hydrogen has +1 because it's bonding with water, and oxygen has a -2. But when you do that, you immediately have a conundrum that this is a neutral molecule, but you have, let's see, 2 hydrogens +2, 2 oxygens at -2, -4. So this would end up with a -4 total net oxidation state, and that's not the case because this doesn't have any charge. So there's a conundrum here. And the conundrum is because if you actually look at the structure of hydrogen peroxide, the oxygens are actually bonded to each other. That's where the peroxide comes from. And then each of those are bonded to a hydrogen. So in this case, especially in a first-year chemistry course, the peroxide molecules, especially hydrogen peroxide, tends to be that one special case. There are others, but this is the one special case where oxygen does not have a -2 oxidation state. Let's look at this and try to figure out what oxygen's oxidation state would be in hydrogen peroxide. So in this case, hydrogen-oxygen bond, oxygen's going to hog the electron, and hydrogen's going to lose it. So it's going to have a +1 there. Same thing on this side. Oxygen, at least on this bond, is going to have a +1. It's going to gain an electron. What about from this other bond with the other oxygen? Well, there's no reason why one oxygen should hog the electron from the other oxygen. So there's not going to have any net impact on its oxidation state. So in this case, this oxygen's oxidation state is +1. This oxygen's oxidation state is also +1. So each of the hydrogens have a oxidation number of +1. Each of the oxygens have an oxidation number of -1. And so you have a net of 0. 2 times +1 plus 2 times -1 is 0. So that's just a special case and it's a good one to be familiar with. Let's do another one, iron 3 carbonate. And now for the first time, I remember when we first encountered iron 3 carbonate, you probably thought, hey, why is it called iron 3 carbonate when there are only 2 iron molecules here, or 2 iron atoms here? And you're about to learn why. Let's look at the oxidation numbers. So oxygen's oxidation number tends to be -2. -2. Now, if carbon is bonding with oxygen, let's look at the periodic table. We have carbon bonding with oxygen. Carbon can go either way. Carbon, sometimes it likes to give away electrons, sometimes it likes to gain electrons. When carbon is bonding with oxygen, this right here is the electron hog. If we had to say who's taking the electrons, it's going to be oxygen, right? So carbon is going to be giving away its electrons. But how many electrons can carbon give away? Well, let's see. It has 1, 2, 3, 4 valence electrons. So the most it can really do is give away 4 valence electrons. So let's go back to the carbonate. So the carbon can at most give away its 4 valence electrons. So what will be the net oxidation number for the carbonate molecule, for the CO3? So this is a +4 oxidation, because it only has 4 to give away. If it's bonding with oxygen, it's going to give them away. Oxygen is more of a hog. Each oxygen has a -2. So let's think about it. I have +4 minus 3 times -2, right? I have 3 oxygen molecules. So I have 4 minus 6 is equal to -2. So we can kind of view it as the oxidation number for the entire carbonate molecule is -2. Now, if the entire carbonate molecule is -2, its contribution to the oxidation state for this entire to this whole kind of the carbonate part of the molecule, we have 3 carbonate molecules. Each of them is contributing -2, so I have a -6 contribution. If this is -6 and this is a neutral molecule, then our two irons are also going to have a +6 oxidation state, because it all has to add up to 0. If both ions combined have a +6 contribution to oxidation state, then each of the ions must have a +3 oxidation. Or that in our hypothetical world, if this happens, at least 3 electrons are going to favor the carbonate from each of the irons. So why is it called iron 3 carbonate? I think you may have figured this out by now. Because this is iron in its 3rd oxidation state. Iron, a lot of the metals, and especially a lot of the transition metals, can have multiple oxidation states. When you have iron 3 carbonate, you're literally saying this is the 3rd oxidation state, or iron's oxidation number in this molecule will be +3. Now, let's do another one. This is interesting. Acetic acid. I think this is the first time that I've actually shown you the formula for acetic acid. You have well, I won't go into the whole organic chemistry of it, but let's try to figure out what the different charges are, or the different oxidation states. So we can just go look. If we just had this, let's say sometimes you'll just see it written like this. You'd say, okay, oxygens, each of those are going to have -2. -2, -2. Hydrogens are each going to have +1, +1, +1. So how are we doing so far? We haven't included. So these oxygens are going to contribute -4. And then the hydrogens, here you have +3. And then here you have +1. You add these up and you get to 0. And you're like, oh, so the carbons must have no oxidation state. They must have an oxidation number of 0. Because they're obviously, we're already at 0 if we just consider the hydrogens and the oxygens. So let's look at that and see if that's actually the case. Let's see. So when carbon is bonding with hydrogen, who's going to hog the electrons? When carbon is bonding with hydrogen, electronegativity, as you go to the right, carbon is more electronegative. It likes to keep the electrons or hog them than hydrogen. So hydrogen is going to lose the electrons in our oxidation state world. It's actually a covalent bond, but of course we know that when we're dealing with oxidation states, we pretend that it's ionic. So in this case, your hydrogens are going to lose electrons. So they're each going to have an oxidation state of +1. That's consistent with what we know so far. And actually, that's another thing. When I did this exercise right here, I immediately assumed oxygen, the hydrogen, I mean, has an oxidation state of +1. And I did that because, oh, everything else in the molecules, carbon and oxygen, which are more electronegative than the hydrogen. So the hydrogen is going to go into its +1 state. If over here I had a bunch of alkali and alkaline earth metals, I wouldn't be so sure. I'd say, oh, maybe hydrogen would take electrons from them. But anyway, so these all gave an electron to this carbon. So just from these hydrogens, that carbon would have a +3, sorry, a -3 oxidation state, right? These lost electrons, this guy gained 3 electrons, so his charge goes down by 3. The carbon-carbon bond. Well, there's no reason one carbon should take electrons from another carbon. All carbons are created equal. So there should be no transfer here. So this carbon's oxidation state is 3. Now what about on this side? So we know that oxygen and hydrogen, this hydrogen is going to have a +1 oxidation state. It's going to give its electron to this oxygen. This oxygen, like most oxygens, are going to take 2 electrons, one from the carbon, from this carbon, and one from this hydrogen. So it's going to have a -2 oxidation state. This oxygen is also going to take 2 electrons. In this case, both of them are going to be from this orange carbon. So it's going to have a -2 oxidation state. So what's the oxidation state of this carbon? It lost 2 electrons to this guy up here, and it lost 1 electron to this oxygen down here. Remember, this guy got 1 electron from the carbon and 1 from the hydrogen. So it lost 1 electron here, 2 there. It lost 3 electrons. So in that reality, it would have a +3 charge. So it turns out that the average oxidation state for the carbon and acetic acid is 0. Because if you average -3 and +3, you get to 0. And that's why I said, oh, maybe these are 0. But if you actually write out their oxidation numbers, this green C has a -3 oxidation state, and this orange C, this orange carbon, has a +3 oxidation state. If you got this one, and I don't think it's overly complex, you will be an oxidation state jock. So I think you're all set now. In the next video, we're going to start exploring oxidation reduction reactions.